Now, if we look at the efficiency of the Carnot engine, the definition of the efficiency can be applied for any process. So we have that E is equal to 1 minus QC over QH. This is the general definition of the efficiency. However, it can be shown that the ratio of QC over QH will equal to the ratio of the TC over TH, where TC is the temperature of the cold reservoir and the TH is the temperature of the high reservoir in the Carnot cycle. So we can have the efficiency for the Carnot cycle, for the heat engine that operates under the Carnot cycle, as the 1 minus Tc over Th. And this is the maximum theoretical efficiency of the heat engine. So this expression is the expression for the heat engine. Now we can use the Carnot cycle for the heat pump also, as we have discussed that the heat pump is just the reverse process of the heat engine. So it means that we can reverse the process of the Carnot cycle to create the ideal heat pump. And for the heat pump that operates under the Carnot cycle, in the heating mode, this is the definition of the COP for the heating mode, right? We have discussed this expression before. But when we do little mathematics, do little algebra, we can rearrange the expression for the COP in the heating mode to be like this: 101 minus QC over QH. And it can be shown that, as in the case of the Carnot cycle, that QC over QH in the Carnot cycle only, okay, we have that QC over QH is equal to TC over TH. So we put QC over QH equal to the TC over QTH here, and rearrange this expression to get that the COP of the heating mode of the heat pump that works under the Carnot cycle is equal to the TH over TH minus TC. So this is the COP for the heat pump under the Carnot cycle. And using the same process, we can calculate the COP for the heat pump in the cooling mode as the Tc over Th minus Tc. So this is the ideal value of the COP for the heat pump that working under the Carnot cycle.